All right. Well, hello, everyone. Thank you for joining us today for our YouTube live event, Chasing Water. My name is Jacqueline Drakis, and I'm the Expeditions Manager for Earth Echo International. We are so excited to have classrooms from all over the globe joining us today as we learn about how NASA monitors water from space. This live event is part of our Earth Echo expedition, Water by Design. Water by Design is a set of videos, resources, design challenges, and STEM projects for students to use to get a better understanding on water resource management, water scarcity, and drought. We're excited to share these materials with you, teachers and students, for no cost at our website, www.earthecho.org, and that's thanks to our sponsor, the Northrop Grumman Foundation. So before we get started today, I wanted to go over a little bit of housekeeping with you all. We love participation during our live events, and there are two ways that you can participate. The first way is to use the Q&A app on the YouTube, if you're watching on YouTube. If you're watching on earthecho.org, there is a form called Question Form right under where you're viewing the live event, and you can go ahead and enter questions now and during the live event. We will try to get to those questions as Dr. Weiss is presenting. We will leave some time at the end for questions as well. And any questions that aren't answered, I will make sure I get you an answer for your question. So today joining us, we have 7th and 8th grade students from Coventry, Ohio. Go say hi, guys. From Mr. Trogan's class, thank you for joining us today. And our special guest and host today is Dr. David Weiss. He's a navigation engineer, and he is live from NASA's Jet Propulsion Laboratory. Go ahead, Dr. Weiss.
Hi, everyone. How's it going? Really thrilled to be here today, and thanks for the invite from Jacqueline. I'm excited to share with you some of what we're doing at NASA to monitor the Earth's water cycle. So Jacqueline asked me to give a quick bio about myself. She thought some of you might be interested. So I'm originally from Texas. I grew up in a small town, Gainesville in north central Texas. I think I have maybe my alma mater is watching, so a special hello to you guys. And I originally became interested in space at a really young age. My mom got me a book by Sally Ride. She was the first American woman in space. I think I was about 4 years old, and I couldn't get over the fact that these people were floating in space. And so from that point on, I kind of latched on, and I always wanted to be an astronaut when I grew up. So I kind of pursued that path. And when it came time to go to college, I decided to study aerospace engineering because I figured an astronaut must have to know something about aerospace. You know, I didn't know any better, but it was a really good path. And I decided to stay in college for about 11 years, got my PhD. And now I am working at Jet Propulsion Laboratory out in California. It's one of the NASA's kind of more research and development centers. And JPL, that's what we call it for short. A lot of people, you might know us for putting the rovers on Mars and most of the other satellites that go to other planets, JPL is a big part of. And I work on an Earth observing side, which is what we're going to talk about today. So maybe we can go to the slides and I'll start the presentation. So are the slides up, Jacqueline?
Yes, you're all set.
Okay. So so the first slide is a video. So I don't see it on my end. Is it playing?
There we go. It's coming. There we go.
Okay, it's really tiny, but that's okay. Maybe I can make that full screen. Okay, there we go. Yeah, so this is an animation of all of the satellites that NASA has that are orbiting the Earth. That we're not going to other planets. We're literally just looking at the Earth and observing the Earth. And so you might ask, why do we do this? Well, space is a great way to see what's going on in the Earth very quickly. One of these satellites goes around the Earth in about 90 minutes. So it's going over 17,000 miles per hour really, really fast. This is kind of a zoom out. So you can go to the next slide now. And so one thing NASA is interested in, we're interested in seeing what's happening with the Earth. How many of you guys have heard about climate change? Yes, a few hands. So, okay, so one thing that we're really interested in knowing about, humans, we use a lot of energy, right? When you turn on the light bulbs, when you turn on your computer, you turn on the air conditioner, all that uses energy. And so where does that energy come from? Most of what we, most of the energy today comes from burning what we call fossil fuels. So it's like coal, oil, natural gas, and go to the next slide. And when we burn these fuels, what happens is that it releases a gas into the atmosphere called carbon dioxide, or here CO2. I put all these little bubbles of CO2. And so you can't see the carbon dioxide. You wouldn't really know it's there unless you're measuring it. But it basically, it builds up in the atmosphere to levels. Go to the next slide and we can talk a little bit about that. So this is, so what we're interested in is what happens when we build up the carbon dioxide. And what I want to leave you with is when we build up the carbon dioxide, basically the temperature goes up as well. And this is a graph that I'm showing. It goes back 800,000 years, so almost 1 million years. And that blue curve is kind of tracking the level of carbon dioxide in the atmosphere over time. And the red curve is temperature. And you can see that carbon dioxide and temperature really follow each other. The other thing you see is that carbon dioxide is kind of within a bound. It's, it's kind of in this normal level. And now, since after 1940, you see this dot where 2018 is, and you see that we're way outside of anything, say, normal that the Earth has seen in the last recent history. And so go to the next slide. And so this is kind of a zoom in on the last recent history when you know people that are alive. And the big black curve is temperature. So what we see is that the temperature is going up as we expect, as the carbon dioxide increases. And I just put the last 4 years there on, and each 4 year has been like a record in the record that we see a record warm temperature. So it's what we expect with the increasing carbon dioxide levels. So go to the next slide. So one thing that we're interested in at NASA is as the temperatures rise because of the carbon dioxide, what happens to the water cycle? We all need water to survive and live. And why do we care? Why do we care about this? So go to the next slide. This is a picture taken from one of NASA's satellites, and it shows the Earth as seen from space. And what you see is it's blue. We live in a water world. Some 2/3 of the surface of the Earth is covered in water. You think there's water everywhere. Go to the next slide. But if we take the water and we shrink it all up and put it in a sphere kind of on the Earth, you see that big sphere, that big blue sphere there in the middle of North America. That is, if you took all the water on the planet and put it there, that's kind of how big it would be relative to the Earth. And if you see that smaller sphere off to the right, that is indicative of all the fresh water on the planet. So that's your water that you see in the lakes and in the rivers, and your groundwater, water underneath the ground, typically water that you would think that you could use. And then if you see, there's a little tiny dot just below that medium-sized sphere, and that little dot is actually all of the what we call surface water. So that is water basically in lakes and rivers on the Earth. And that is what most people think about when you think of where you get your water to drink from, for instance. And so that's water for 7 billion people. So the point here is that this is, there's a finite amount of water. There's only a certain amount. And so we need to make sure we know where it is and where it's going and what's happening to it, so it's in the right places and we can use it for what we need. Okay, go to the next slide. And so this is a schematic. I want to just kind of give an overview of the Earth's water cycle. You guys have probably learned about this a little bit, but basically the water is always moving in the Earth. It's a very dynamic system. On the right side of the graph, there's water stored in the oceans. That's where most of the water is. So the oceans, the sun will hit the oceans, and that causes some water to evaporate, and it raises up into the atmosphere, and then that water will condense and form clouds. And if you get enough clouds, then it'll turn into rain. It'll rain and snow. And so when that rain and snow falls, some of it falls right back into the ocean. And then the stuff that falls on land, it can either form an ice sheet, or it will fall as snow if it's cold enough, or just regular rain. And then some of that water will end up as a river. It will run down the mountains and into a river. Some will end up in a lake and will store it in the lake for us to use. And then additionally, water will soak into the ground. And you don't really think about the water or the ground as storing water. But actually, if you just take a shovel and you dig into the dirt and you pick it up, it's actually pretty moist usually. There's some moisture in there. And we call that soil moisture. And we're really interested actually in knowing how moist the soil is, because that can tell us how good crops can grow, for instance. And then some of the water will even go past the soil into, further and further down into these groundwater reservoirs. And we use a lot of groundwater actually for growing crops as well. And I'll talk a little bit about that later. So NASA's interested in knowing all of these components of the water cycle. So there's a mission dedicated just to measuring how much rain there is. And there's a mission, it's just to know how much snow is falling. And we have another mission that's just looking at the soil moisture. How wet is that soil? And so I'm going to talk about a mission that I work on and that we work on called GRACE and GRACE Follow-On, that measures basically all of the storage terms. So all of the orange dots that you see in this figure, we're measuring all those at the same time. So anywhere that water is stored on the Earth. So go to the next slide. And we measure this, I mentioned, with a satellite mission called GRACE. And GRACE operated from 2002 until last year when it died. So it was operating for about 15 years. And then we have a new mission called GRACE Follow-On, which is launching just next month in about 3.5 weeks. I'm really excited. And I'll tell you at the end of this how you can watch the launch and follow along. And it's going to continue the work of GRACE. And so now I am going to show you a little demo. We're going to do a little science experiment. We'll show you a demo of how GRACE works and what we're doing.
Dr. Weiss,
Yeah.
First of all, we just wanted to say hi to NASA Langley. They're watching and they said hello. So we want to say hi back.
Hi, NASA.
And we also had a question from the audience. How many missions are there related to water? Do you know the number?
That is a very good question. I don't know the number. And NASA's not the only one. So the European Space Agency, for instance, has several missions that are also related to water. As well, but I would think upwards of maybe a dozen, worldwide that the governments are funding.
Excellent. All right, go ahead.
Okay.
Thank you.
No problem. Okay, so so to tell you how GRACE and GRACE Follow-On works, I want to start with a science experiment. So I brought a ball today, and I'm going to make this ball disappear when I count to 3. Okay, ready? 1, 2. No, I'm just joking. This is science, not magic. Okay, so we're gonna do it again though. Okay, ready? 1, 2, 3. Okay, and so the ball dropped out of my hand, and this happens every day. This is nothing really fancy, but if you ever think about what's actually happening when something drops, what are the physics behind it and what's going on? And no one knew this until about 350 years ago, when Isaac Newton discovered what he called gravity. So the story goes, he's sitting under an apple tree, an apple falls out of the tree, bonks him on the head, and he said, why did that apple fall out of the tree? So it turns out there's this force called gravity, and I'm going to use the whiteboard here. I'm going to write a little math equation, so we can say, Fg, this is the force of gravity, for instance, is equal to, let's see if you can see that. a big G, which we know this is just a constant, and then a mass of object 1, and then mass of object 2, and then we divide by the distance, r, between them, and we square it. So the point is that every 2 objects in the universe, any 2 objects, you know, let's take an example between you and your teacher right now. There's a gravitational force between you guys, and you can figure out exactly what that is. All you need to know is how much you weigh, how much your teacher weighs, and how far apart you are. And then you can plug those into this formula and figure out the gravitational force acting between you 2. So if we go back to the ball, you know, when I drop this, I'm not pushing it, I'm not throwing it, but there's gravity acting on it from everything, from me, from the chair I'm sitting in, from my, you know, from the table, even from you guys, you know, but it's really tiny. But the biggest force is actually from the Earth. So the Earth is really massive. It weighs a whole lot. So there's a force between the Earth and this ball, and since the Earth weighs so much, it actually pulls the ball down, and that's exactly why it drops. It just goes down whenever I drop it. So that's what gravity is. So we use gravity in space. We measure gravity in space using these satellites. So I've got a little mock-up here of how the GRACE and GRACE follow-on missions work. And so the way it works is there's two satellites, and they're identical. And I'm going to take one of these off and just show you real quick. So it's kind of a trapezoidal shape. It's a very sleek design. It's got these solar panels, covered in solar panels, which gets its power from the sun. And it has some, this is kind of this is a GPS antenna, so we can figure out exactly where we're at. And then here on this side, this is the main science instrument. This is called a microwave instrument. And so what happens is these 2 satellites are in a formation, and we put them such that one follows the other at all times. They're separated by about 150 miles, so that would be like one being in Los Angeles and one being in San Diego. And all we do is we track the distance between these over time. So this microwave instrument I was talking about, all it does is measure back and forth. How far apart are you at all times? And that's really valuable information, it turns out, because in space, now let's pretend that this ball is a mountain, for instance, and it has a lot of mass, okay? So now I'm these 2 satellites. Let me back this up a little bit. And we're going to fly over. And so as the first satellite gets to the ball, it doesn't actually drop down when you're in space, because it's going, remember, it's going 17,000 miles an hour up here. And so what actually happens, though, is it feels the ball. It feels the ball because the ball weighs more, or it feels this mountain, and it causes it to speed up relative to this one back here. And so as it speeds up, it changes the distance between these 2 satellites. And then it keeps going, and now this satellite, the mountain is behind it, so it pulls it back a little bit, and again, it changes the distance between these 2 satellites. And then the same thing happens with the satellite, the second satellite. Now it feels the mountain, and it speeds up relative to that first satellite, and so it changes the distance. So these 2 satellites are always doing this dance back and forth as they go around the Earth, as they go over mountains, rivers, lakes, etc. So you can imagine now, you fly over the same place on Earth every single day. And what you're doing is you're basically weighing the Earth in that location every single day. You're taking a weight measurement of the Earth. So if it snows on a mountain, the mountain accumulates snow, and it'll weigh more. So then we see that with the satellites. And then when the snow melts, the mountain weighs a little bit less, and then we see that with the satellites. And that's really all that we're doing with this mission. But it allows us to do some really, really cool things and learn some cool things about the Earth that I'm going to talk about next.
So Dr. Royce, we had a question from Paige. Why do the satellites go so fast around our planet, around Earth?
That's the speed. If they didn't go that fast, then they would fall back to Earth. So that's the speed that you need to stay in orbit. And that's why we need to put these on a big rocket and get going super fast to achieve what we call orbit, an orbital velocity.
Awesome. I'd like to give a shout out to Ocean View 6th graders. They're watching us. And then we have a question from Gainesville. They say hello.
Oh, hi, Gainesville.
They would like to know, why are the GRACE satellites that trapezoid shape?
It's mostly for what we call drag. So you don't think about this, but even in space, there's particles. You know, if you go outside, you can feel the wind blowing. There's air particles, but those particles are the same in space. And so what we want is that for a pretty sleek design, so it doesn't, so the drag doesn't slow it down too much. Because, for instance, the reason the first GRACE satellites ended, that they died last year, is that you put the satellite up pretty high, and over time it keeps going around and around and around, but it keeps hitting these particles just a little bit. But over time it makes it go down a little bit and a little bit more and a little bit more. And so for GRACE, that, you know, the end of life was about 15 years when it just couldn't stay up anymore. But that was all from the drag. So this kind of minimizes the drag, and then they're the same shape because we want the exact same drag force acting on them, so we can take that out when we process the data.
Excellent, thank you.
Yeah. Okay, so if we go back to the slides, then we can go to the next slide. And yeah, so this is basically what we learned with GRACE. So this was 15 years of GRACE gravity fields. And so each little circle there is a picture of the globe. And it's the gravity field for that month and that year. You can see on the top, we have the month, and on the side, we have the year. And this is one of my favorite pictures. If you just go back and you like squint your eyes, you can kind of see a lot of red on the left side and a lot of blue on the right side. And so what that is actually this annual exchange of water between the oceans and the lands, or in the land. So from, you know, January to May, the oceans are kind of red. That's kind of what you're seeing. And that is a water deficit. So not as much water in the oceans, more of it is on land. And then vice versa, later in the year, there's actually more water in the ocean and a little bit less on the land. So that's we're tracking the annual water cycle. But what we're really interested in is how are things changing over a long term. And so what people like to do is they stack these months up one after another, and we want to see how are things changing over a long time frame. And so if you go to the next slide, you'll see exactly this. So this is kind of a stack of each one of those little globes from 2002 until 2016. And we call this a trend plot. But what it is basically, on average, how have things been changing every year? And you'll see a bunch of blues and a bunch of reds. And all the blue spots are where there's been extra water, where we're gaining water. And all the red spots are where we're losing water. And so, you know, there's a story behind each one of these spots, each red spot and each blue spot. But if you look at this map, there's really three themes that emerge. And the first theme is we see an unsustainable use of groundwater around the globe in many areas. And I've circled each one of those here in black where we see that. And one is right here in California. So I say an unsustainable use of groundwater, so we're basically pumping out groundwater to, say, grow crops or to drink. And in a healthy system, that groundwater would get replenished. It would rain, it would soak through the ground and go back in and recharge. And so we would see, you know, some ups and downs, but over a long term, it would be pretty flat. And so here what we're seeing is we're pumping out more than what is being replenished. And so that can be problematic because groundwater is a finite resource, and there's only a limited amount. So when it runs out, it runs out. So it's something we need to be very aware of. I think about 50% of the world's crops are grown with groundwater, so about 50% of the food you eat, and about 50% of the people rely on groundwater for their drinking water. So it's a very important resource. So if you go to the next slide, this is an animation. It's a video, and it's going to show what's happening right here in California, where I'm at. And we have a problem with groundwater pumping here. And this is the GRACE data over time. And you'll see California gets kind of blue and red. Blue are years whenever we had extra water. And then red here, we're going to go into a little bit of a drought in 2018 to 2010. Then we get a really nice winter in 2011, great snow for skiing at Mammoth. And then we go back into another really harsh drought that kind of peaked in 2015. And a lot was in the news about that. And then we had a big winter, which kind of brought us back out of the drought, which is where we're at now. We're kind of in a normal state. But you can see this kind of a longer term still decline, and a lot of that is due to groundwater. So we go to the next slide. Okay, so that was the first theme, groundwater. The next
Dr. Weiss?
Yeah.
Before you go to theme 2, I just had a question from Adams Elementary in North Carolina, and they want to know, how does NASA know if a satellite is working? So how did you guys know that the original GRACE stopped working?
That's a great question. So we have, if you've ever seen these big antenna dishes that are on the ground, we can communicate and we can talk to a satellite. So we can basically send a command. If I bring back my little model of the satellite, you see this little thing sticking out here on the bottom. This is what we call an S-band antenna. And this is what we use to transmit all of the data back to the Earth. So we get all of our gravity information and any health of the spacecraft. So we basically are always asking the spacecraft, hey, are you healthy? Are you healthy? Are you healthy? And anytime we fly over where there's a station that we have we call a downlink, it'll send us some information and say, yes, I'm healthy, or no, I'm not. And when the GRACE satellites died the first time, we knew that was coming. It was expected. So, and I should mention also that the satellites were actually only designed to last 5 years. So the fact that we got 15 years out of them was pretty incredible, and a testament to a lot of people here at NASA that worked hard to keep them up for that long.
That's excellent. And just one more question about the GRACE follow-on, since you have the model out.
Yeah.
Would those satellites ever touch each other? Is that possible? And what would happen if they did? And that's from Salcombe Valley Elementary School. Yeah,
that's a great question. The answer is yes, they could if we fell asleep at the wheel. And if they did, it would not be very good. But we are very careful that they do not. So 200 kilometers apart or 150 miles it sounds pretty close, but it's far enough away that we're not really too worried about it. But that is one thing that we do all the time is we have to monitor where everything in space is. Remember all those satellites I showed on the first slide? If I showed you an animation of all the satellites that are orbiting Earth, it would look like, I mean, it's just so filled up. There's so many satellites. And so we have to know where everything is at all times, and we have to predict if our satellite will impact any of those satellites. And if they're on a collision course, then one of the satellites will have to move and say, same thing when you stop at a stop sign. And so we always have to monitor that. And if they did hit, then they would, when satellites hit, it's happened a few times, everything explodes and there's little pieces everywhere, and then we don't know where those pieces go. And it's important that we know where all the pieces are so they don't hit other satellites and start this big effect.
And one other is, we had a question on how are the satellites powered, and that's by the solar panels, correct?
Solar panels, yeah. We have solar panels, and the solar panels charge batteries on board. And then so if we're in a period where they don't get a lot of sun, then the batteries work and give the satellites power.
Excellent. And the Salcombe Valley Elementary School has a lot of questions about glaciers, but I think you're going to answer them, so I'll let you keep going on.
That's where we're going right now. So if we look at this map, the second theme that emerges is that the ice is melting. So on the bottom here, I put a figure. All of the places in yellow, if you've ever wondered where is there ice in the world, this is a picture of that. And there's two big ice sheets, Greenland kind of at the top and Antarctica at the bottom. And these are really vast reservoirs of ice. So we keep a close eye on these. And then all of the other yellow spots, these are land-based glaciers, so mountainous regions that have permanent ice. And if you look at the top plot, basically everywhere that there's yellow, it's red that we see in the GRACE data. So that means the glaciers are losing mass, that ice is melting. So if you go to the next slide, so the next question is how much ice is melting? You know, how much? And we use a term called gigaton. Okay, so it's I didn't know what a gigaton was until a few years ago too. But it's a gigaton is 1 billion tons. It's a huge amount. And this block that is drawn here on overlaid on New York City, that would be 1 gigaton of ice. Just to put in perspective, it would be a massive block of ice. So we can go on to the next slide. And this is a video of what's happening at the Greenland ice sheet. And what you're going to see is, let's see if it will play. But Greenland is going to turn progressively red over time, kind of on the edges, and that's places where it's losing ice. That ice is melting, and you can see on the right side this time series where we're going up and down and up and down. And what that is, that's an annual cycle of water on Greenland. So basically, it snows in the winter. It's really cold, and all that snow accumulates, and Greenland weighs more, and we measure that. But then in the summer, a lot of that melts, and it goes down, and that's what's making it go down. So basically, more is melting every year than what is being replenished with snow. And so over a long term, that causes the total mass of Greenland to be negative. And it's about, here it's about 280 gigatons every year. So 280 of those big blocks of ice are being lost from Greenland every year. So we go to the next slide.
So Dr. Weiss, we have a question from an elementary school, and they want to know, does the melting of the glaciers hurt the animals and the environment around them?
It definitely changes the environment around them. So if they're, they've kind of adapted to whatever environment that they're used to, so it definitely changes things. Absolutely.
And then is there a way for us and the students watching to help stop the ice melting?
There is. I actually have that's kind of a complicated question, but yeah, a lot of this is tied to, as you can imagine, the warmer temperatures we talked about. Remember, the temperatures are going up. And as you would know, I mean, when things get hot, ice melts. So that's basically what's happening. And the temperatures are going up because the carbon dioxide is going up. So a lot of people talk about carbon footprints, like how much carbon do you use as an individual? And there's certain things that you can do. I actually have a slide in the backup that someone else put together. We could go to that now, or we could get to it right when I'm done.
Yeah, we can go to it at the end. Yeah,
okay.
We can keep going.
So we can go to that right when I end, and we'll go to that, and I'll come back to what some people have said or some choices that you could make.
Perfect, thank you.
So back to the ice. These two figures are from the two ice sheets, these two big ice sheets on the Earth. And they're both losing. Greenland is about 286 gigatons every year, and Antarctica is about 127 gigatons every year. And if you look at all the ice in the globe, it's like 600 of those big blocks every year. So, another way you think about this, I don't know if you guys have seen these little Mini Coopers, these tiny cars. This would be equivalent to about 2,500 of these being melted every second. So like 1, 2, 3, 4. It's like 10,000 of these frozen Mini Coopers were just melted. Okay, and so that's the amount that we're talking about. So when the ice melts, where does it go? There's really only one place for it to go, and that is into the ocean. It drains off and goes into the ocean. So if we go to the next slide, that is the third theme that we see in this map, is that the oceans
Dr.
are
Weiss, real
predominantly
quick,
blue. Yeah.
before we get into oceans, because I think this is going to lead to it. We have a lot of people asking, do you know how many gigatons of ice there are in the whole world?
A lot.
A lot, many gigatons, right?
Yeah, I do. So I can put that in perspective a little bit. So Greenland has the potential, if all of Greenland melted, so this, I'm going to kind of talk ocean and ice here. So lots of times we think about the ice melts, it goes into the ocean. So if Greenland, all of Greenland melted, it has the potential to raise the sea level, the oceans, by 8 meters. So that's about 25 feet, or 8 yards and meters are pretty close. And then Antarctica is about 70 something. So somewhere around 80 meters, 250 feet. So close to the size of a football field in terms of how much the ocean would go up. But that won't happen anytime soon. That would be a whole lot of ice to melt. And I would have to calculate how many gigatons it is.
Okay, thank you.
Yeah. So the third theme we see is that the oceans are rising. They're blue. So the ice is going into the oceans and it makes the oceans go up. So you can go to the next slide. And this is what I call the bathtub effect. And so this is additionally some data from GRACE that we measure. And basically since 2002, the oceans have gone up 1 inch. So all those gigatons we were talking about, it's only caused the ocean to go up 1 inch of the extra water that's being dumped into it. Okay, but that doesn't tell the whole story on the oceans. If you go to the next slide, there's really 2 effects that are happening to the oceans or sea level. One is the bathtub effect. The ice goes into the ocean goes up. And then the other is something we call thermal expansion. So remember, the temperatures are going up, so everything's warming up. And if you do a little science experiment at home where you take a bucket of water and you just heat it up, you'll see that the water actually expands. So as water heats up, it expands. And so that's happening to the oceans. The oceans are absorbing a lot of extra heat and they're warming up, so they're expanding. So you get these 2 effects. One is a bathtub effect and one is this expansion effect. And in total, if you're sitting, on the beach and you just bring a ruler out there every day, for the next however many years, you would see that the sea level is going up about 1 inch every 7 years. So you might think, man, who cares? 1 inch. That is a really tiny amount over 7 years. So if you go to the next slide.
And Dr. Weiss, just so you know,
Yeah.
we are at about 40 minutes, so we might lose some viewers, but I just want to let everybody know watching that we'll send out resources afterwards, but we'll let you continue.
Okay, I will wrap up. I'm almost done. So the point here is that inches do matter. Currently, this is a picture of, say, what Miami Beach looks like currently. If the oceans were to go up 2 feet, so 24 inches, everywhere in blue would be places that would be underwater. And then 3 feet, you would see a lot more underwater. And I picked these 2 and 3 feet numbers because kind of the best estimates for where how much the oceans will rise by, say, 2100 by the end of the century right now is about 2 feet. Some experts would put it closer to 3 feet, but there's a lot of uncertainty here. And this is something that we're really trying to understand better, is how much will they go up and how quickly? And that's why, go to the next slide, we're launching this new mission called GRACE Follow-On. And it will continue this time series of measurements. Hopefully, the first data will be in June of 2018. And if you go to the next slide, we are going to be launching on May 19th at 1 o'clock Pacific time. You can follow the launch live at this website, nasa.gov, NASA Live. There's a lot of information on GRACE Follow-On here at this website. And I will show you, that's kind of the end. I have a few pictures of the satellites I thought you guys might want to see. So if you go to the next slide, this is the real spacecraft, and basically we've taken the solar panels off, and this is what it looks like inside. It's packed, wires everywhere, instrumentation. It's really packed. You go to the next slide. you can see these are people kind of standing by it, so you get a sense of how big these satellites are. And here they're doing some testing on the satellites. You go to the next slide.
And do you know how much they weigh?
Yeah, about 1,200 pounds, I think.
Each?
Each, yeah. And this is another cool picture of them. So I will, if you go to the next slide, I will end. Oh, yes, this is, I want to end on this note. This is a picture taken from the Cassini spacecraft of Saturn, one of my favorite pictures. It's absolutely gorgeous. And if you zoom in this image, go to the next slide, there's this little dot. And that little dot right there is what we call home. That's planet Earth. So when you zoom out, that's where everyone's lived that we ever know. So we want to keep a close eye on it and know what's happening so we can preserve it for generations to come. And that will end there.
Thank you so much. I'd like to go to Mr. Trogan's class and see if you have some questions you would like to ask Dr. Weiss. Don't forget to unmute yourself.
Okay. I think we're good.
All right.
Yeah.
We can hear you. Go ahead.
Yeah. Pearson, you have a question? Loud.
Yeah. As middle school students, what are some immediate actions we can take to make sure we have fresh, safe water for our future?
Did you hear it?
Yeah, so you have, say that again. So what do you have?
Come up here.
Don't be shy. Come be on camera.
So,
all right.
As middle school students, what are some immediate actions we can take to make sure we have fresh, safe water for our future?
Yeah, fresh, safe water. That's a good question. I'll go to if you go 2 slides forward, we kind of talked about this, maybe some things that you can do. Go to the next slide. So this is a graph that was put out last year by some researchers, and these are kind of individual actions you can take to, say, reduce your carbon footprint or reduce, how much fossil fuel that you consume, which would then lower temperatures, which would then, say, help, the ice stop melting, etc. And some simple things are, upgrading light bulbs, hanging dry your clothes, recycling, washing your clothes in cold water. And then, other things are, try to bike instead of driving your car when you can, or it's kind of those kind of actions that can have an impact.
All right. You guys have another question?
Yeah, we have one more from Kyle. Go ahead.
Yeah. How does the flight path of the satellites affect the data that's collected?
Yeah, great question. I could answer that for a whole hour. That's what I do for my job. But basically, the satellites are in what we call a polar orbit. So they go, if this is the Earth, they go over it like this. And so as we go over it, the Earth is rotating beneath it. So that allows us to sample everything as the Earth rotates beneath it. And so we're kind of, where we fly over and when we fly over it, we don't really have a lot of control over it. We're just flying over it. And there's a lot of other intricacies that we could go into, but you probably aren't that interested in those. But they're very coupled. It's very important.
So could you review how satellites are actually launched?
Yeah, sure. Actually, if you go back to one of those pictures, go back. Yeah, right there. Go forward one. So these satellites, go forward one more. They're going to be in a rocket. Basically, we're going to launch on a SpaceX Falcon 9 rocket, and this thing, they're mounted like this. See how they're kind of coupled together like that. You stack them together like this, and that's on what we call a multi-satellite dispenser. So we stack them in the rocket, we put it in the rocket, and then you basically light the candle, and the rocket goes off. And within 10 minutes or so, we're already up in orbit, and they shoot the satellites out, and they both come off like this, and then we start commanding, and we try to get them into formation pretty quick. But but that's basically how it works.
Excellent. All right. Well, thank you everyone so much for joining us today. Thank you, Dr. Weiss, for your expertise and your amazing presentation. Thank you, Mr. Trogan, and your students from Ohio for joining us. This presentation will be available on our YouTube page and also at earthecho.org. I would encourage you all to go and check out our Expedition Water by Design materials. They go into a lot of the issues we talked about today, including groundwater and aquaponics and all of those fun things. A big shout out to our sponsor, the Northrop Grumman Foundation, for making those resources available for free on our website. And I'd also like to thank NASA and especially Dr. Weiss for your time today and your expertise. Thank you so much. And we'll see everybody again soon. Have a great day. Thank you.
Thanks, everybody. Bye.
Bye.